I'll get started then with transposes and permutations. So let's let A be an m by n matrix. So this is a matrix with m rows and n columns. And then I'm going to introduce an operation called the transpose. So the transpose of A is just going to be denoted by A with a little t in the subscript. So, just like A squared, this is A transpose. And that just means, so the transpose operation just puts the columns, so the columns of A transpose are the rows of A. So the first row of A becomes the first column of A transpose. The second row of A becomes the second column of A transpose, and so on. And if you think about it in terms of the elements, so a matrix A has elements that are little a sub ij. In the transpose, those would just be A sub ji. So I'm just swapping the indices. And so if I do that, if the dimension of my matrix A is m by n, then if I swap the rows and the columns, the dimension of A transpose is going to be n by m. So here I had n columns. They become the n rows of A transpose. And just, it's a pretty obvious thing to do. If I have A is just 1, 2, 3, 4, 5, 6, so the first row is 1, 2, 3, then the first column of A transpose is 1, 2, 3. And when A is not square, note that the dimension changes too. So it goes from being a 2 by 3 matrix, so A has 2 rows and 3 columns. A transpose then has 3 rows and 2 columns. And so some properties of the transpose. The first one, hope everybody agrees with this. So if I take A transpose and transpose it again, I just get A back. If I have a transpose of a sum, so I have A plus B transpose, that's just going to be equal to A transpose plus B transpose. Gets a little bit more interesting with products. So if I have a matrix product AB, then the transpose of my matrix product AB, so AB, the product transpose, is equal to B transpose A transpose. So this is the same way this happened with inverse matrices. You take the transpose of the pieces of the product, so you get A transpose and B transpose, and then the transposing the product also changes the order. So AB transpose becomes B transpose A transpose. And the transpose of A inverse, so here I have A inverse, and then I'm going to take the transpose of that matrix, and that is equal to the inverse of the transpose of A. So I can swap this A, I can swap the inverse and the transpose operations. And a lot of times you'll see, instead of using this notation where I have to put A inverse in parentheses and then transpose, this will just be written as A to the negative t. And that just means A inverse transpose. Okay. So we can use the transpose operation to define something called a symmetric matrix. So a matrix A is symmetric if it satisfies A equals A transpose. And so first of all, this is only, well, let me see what the next bullet point is. Okay, this is only going to work if A is a square matrix, because the only way A can be equal to A transpose is if the M is equal to N, so that when I transpose it, it's still an N by N matrix. So A has to be a square matrix. So remember I said that what transpose is doing to the elements, it's just swapping these little indices here. So if I have AI are the elements of A, then I need AIJ are the elements of A. I need AIJ to equal AJI. And then when I take the transpose, these two things are going to flip. So that's what this is going to mean. So it means that if I have whatever element is in, say, the 1, 2 position, has to also be in the 2, 1 position. So this is an example of a symmetric matrix. So the diagonal elements, they can be whatever you want because they're not going to change. When I have AII, if I switch the two i's, it's still AII. But the off-diagonal elements, so here whatever's in the 1, 2 position also has to be in the 2, 1 position. Whatever's in the 1, 3 position has to be the same as the value in the, it's not letting me highlight there, has to be the same as whatever's in the 3, 1 position. And then the 4's here have to be the same, so that would be 3, 2 position has to be the same as the 2, 3 position. So here I have A and A transpose being the same thing, so this is a symmetric matrix. And then an even more special case of symmetric matrices is a diagonal matrix. And so a matrix is diagonal if only the diagonal elements are non-zero. So any element, Aij, where j is not equal to I, has to be equal to 0. And so a diagonal element, just because these are going to be, so this is D11, D22, D33. If I switch the order of those subscripts, they stay the same. So diagonal matrix is automatically symmetric. And again, the important thing here, not that it's symmetric, that should be pretty obvious, but that when I have a diagonal matrix, if I take the transpose of it, I just get the matrix back. Okay. And so now I want to explain a little bit where diagonal matrices are going to come from, or sorry, where symmetric matrices are going to come from. So let's let R be any m by n matrix. So here I'm using R just because I want it to be a rectangular matrix, so not necessarily square. So it has m rows and n columns. Then the matrix A that I define as the product of R transpose and R is going to be a symmetric matrix. And so to show that, all we have to do is take the transpose of A and show that that's equal to A. So the way I'm going to do that, I'll take A is equal to R transpose R. So then A transpose is just going to be the transpose of the product R transpose R. And now I want to use the rules that I gave a couple of slides ago for how I can deal with transposes of products. So it basically says I take the transpose of the pieces and I get them back in the opposite order. So this R here becomes this R transpose here. And this R transpose here, well, I take the transpose of that. So it's R transpose transpose, so that's going to become R again. So I have R transpose R, and that's what I initially was calling A. So I can start out with any rectangular matrix, and if I make this matrix product R transpose R, then that product A is going to be a symmetric matrix. And you can do something similar for A equals R, R transpose. Let's see if okay, so I go through this example again. So it's basically the same idea. I've defined A to be RR transpose, and I'm going to take the transpose of that. And if I can show that's equal to A, then A transpose equals A, so A is symmetric. And so the same thing happens. It's just going to swap the two terms. So I have R transpose transposed, so that's where this first term comes from, the first piece of this product. And then here I have an R, and then I'm going to transpose it, so I end up with R transpose. And then the transpose of a transpose is just, I get the matrix back, so that'll be R, R transpose, which is A. So I get R, R transpose is also symmetric. And so what we're going to find as we start looking at matrix factorizations is a lot of times we're going to start out with a matrix R that's rectangular. And we're going to do some calculation where we're going to end up with the product R transpose R or RR transpose, or maybe both of them. And so symmetric matrices are going to show up sort of more often than you would expect just randomly. And there are a lot of nice properties of symmetric matrices that I'll get to later in this set of lectures. And the second type of matrix I want to talk about is called a permutation matrix. again, a permutation matrix is going to be square, so it's an n by n permutation matrix P, has the rows of, so this is I, the identity matrix, but in any order. So the identity matrix, it has the, the first row, the row that starts with a 1 goes on top. The row that has a 1 in the second position goes in the second place. And if I shuffle those around in any way, the matrix that I end up with is going to be a permutation matrix. And so for 3 by 3 matrices, there's 6 possible permutation matrices. So, one of the things I could get when I shuffle the rows around is I could just get the identity matrix back. So we actually are going to count that as a permutation matrix that says just put everything where it is. And then these other ones, so the ones I've labeled 2, 1, 3, 1, and 3, 2, what these matrices are going to do when I multiply, they're just going to swap rows. So where this would be important, when I was talking about pivots when we were doing elimination, it's possible that you could end up with an equation. There's no particular reason why the equations have to be in any order. And so if you had an equation that started out, so you had 0 times x plus something times y plus something times z equals something, and suppose I decided to put that equation first, then I wouldn't have a pivot in the first position. So I probably wouldn't want that to be my first equation in my system. And so this is sort of the matrix way of solving that problem. If I needed to get that row out of the first row, I could multiply by one of these matrices. So for instance, I could swap it with the second row. And the other interesting thing that some of these have is if I multiply P21 by P21, so this is the matrix that swaps the first 2 rows. If I do that again, I would get my original matrix back. So that means that P21 is its own inverse. So it swaps row 1 and 2, but if I do that again, it puts what was originally row 1 back in row 1, and what was originally row 2 back in row 2. The other interesting property that this has is P inverse is the same as P transpose. So for P21, since this is a symmetric matrix, and it's its own inverse, you have this kind of strange, I guess I would call it duality, but there's actually 3 things, so maybe it's triality. You have the matrix, its inverse, and its transpose all being exactly the same matrix. For the more complicated ones, so if you want to swap, more like pairs of rows, then you still have this property that P inverse is P transpose, but you don't have the property that that these are their own inverses anymore. And so just an example of what this is going to do. So the permutation matrix P32, that just swaps the third row and the second row. So if I have a vector 1, 2, 3, so it's a column vector, so the first row is just 1, 2, 3, then it's just going to give me 1, 3, 2. So it took whatever was in the third position and put it in the second position. Whatever was in the second position, put it in the third position. And then if I multiply the output of this, so 1, 3, 2, by the same permutation matrix again, it's just going to swap this 3 and 2, so it puts the vector back in the original order, 1, 2, 3.